The February morning at Kummersdorf testing grounds was bitterly cold, frost clinging to every surface of the captured American tank that sat waiting for its German examiners. It was early 1943, and Hauptmann Friedrich Weber circled the olive-drab M4A1 Sherman with a mixture of curiosity and professional skepticism. This was War Daddy 2, captured from the 1st Armoured Division near Sbeitla, Tunisia, just days earlier, and it represented everything German propaganda had taught Wehrmacht engineers to dismiss about American industrial capability. Weber had spent his entire career in the Waffenamt, the German Army's weapons testing agency, examining captured equipment from Poland, France, and most recently, the Soviet Union. He knew Soviet 34s. He understood the mechanical philosophy behind British Matildas and Churchills. But this American machine was different. As his gloved hand traced the welded hull seams, he felt an unsettling realization beginning to form. Something about this tank didn't match what they'd been told about American manufacturing. German military doctrine had been clear on American capabilities. The Americans were industrial novices, their tanks cobbled together by automobile workers who knew nothing of armored warfare. Minister Goebbels' propaganda broadcasts regularly mocked American gangster engineering, claiming their tanks were nothing more than tractors with armor plates bolted on. German tank crews went into battle believing their Panzer IIIs and Panzer IVs were products of superior Prussian engineering tradition, refined through generations of military excellence. But here at Kummersdorf, far from the front lines and the propaganda ministry's oversight, German engineers were about to discover something that would fundamentally challenge their understanding of industrial warfare. This Sherman tank, this supposedly crude American creation, was about to reveal a logistical philosophy so advanced, so thoroughly considered, that it would expose a critical weakness the Wehrmacht had failed to address in its own armoured forces. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Oberingenieur Hans Richter was the first to climb inside the turret that morning. As a mechanical engineer who had worked at Krupp before the war, designing components for German tanks, he understood what made armour effective in sustained combat. The smell inside the Sherman was different from German tanks, less oil, less the acrid burn of overstressed metal. Everything seemed cleaner, more organised, almost methodical. His flashlight swept across the turret interior, illuminating the gunner's position, the commander's station, the radio equipment mounted cleanly on the turret wall. The 75mm gun was capable, if not spectacular, roughly equivalent to the weapons German tanks had been mounting since 1941. But as Richter began examining the mechanical systems, his trained eye picked up details that made him pause. "Weber," he called out, his voice echoing in the confined space. "You need to document this carefully." What Richter had noticed would become the first of many entries in a comprehensive evaluation report that would eventually reach the highest levels of German armoured command. The gun traverse mechanism was hydraulically powered but remarkably simple. Where German tanks employed complex gearing systems that required precise adjustment and specialised maintenance, the Sherman used a straightforward hydraulic motor that could be serviced with basic tools. Outside the tank, Feldwebel Kurt Schneider, a maintenance specialist who'd kept Panzer IVs running across North Africa, was examining the engine compartment with growing bewilderment. The access panels opened easily, too easily. Massive hinged doors swung wide, providing clear sight of every major component. The Continental radial engine sat cleanly mounted, surrounded by components that were clearly labelled, logically arranged, and obviously designed for rapid replacement. "This is remarkable," Schneider muttered to his assistant. "Look at how everything is positioned. The engine can be pulled straight out. No disassembly of surrounding systems required." This contradicted everything Schneider had experienced with German tanks. On a Panzer IV, removing the Maybach engine required first removing the transmission, then disconnecting dozens of systems, then carefully extracting the power plant through a limited opening. It was a depot-level task requiring specialized equipment and trained technicians. This American tank appeared designed so that field mechanics could perform the same operation. The suspension system revealed another layer of American design philosophy. Weber crouched beside the vertical volute spring suspension, examining the bogies with professional interest. Each road wheel assembly was independent, mounted on simple, robust springs. The track pins were standardized, easily replaced. The entire system radiated a philosophy of maintainability that seemed almost excessive. "They've sacrificed performance for simplicity," Weber noted in his preliminary observations. "The suspension is not as sophisticated as our torsion bars, but it appears extraordinarily resistant to damage and simple to repair." But it was when the German team attempted to catalogue the tank's components that the truly unsettling discovery emerged. Weber had ordered a complete disassembly of selected systems' standard procedure for evaluating captured equipment. As technicians carefully removed parts, labeling and photographing each component, a pattern became apparent that none of them had anticipated. Unteroffizier Franz Müller, responsible for cataloguing parts, approached Weber 3 days into the evaluation with a puzzled expression. "Hauptmann, we have found something unusual about the spare parts." Müller spread out his inventory sheets on a makeshift table in the cold testing facility. "Every component we have removed has standardized measurements. The bolts are all common sizes. The electrical connections use identical fittings. The road wheels are completely interchangeable, not just with each other on this tank, but according to the markings, with road wheels from any Sherman variant." Weber studied the inventory sheets, his experienced eye recognizing immediately what Müller had discovered. "Show me the engine components." Müller led him to where technicians had partially disassembled the Continental radial engine. The parts were laid out in careful order, each tagged and measured. "The cylinders are identical," Müller explained. "Any cylinder can be installed in any position. The connecting rods are standardized. Even the valve assemblies all interchangeable." This was unprecedented in Weber's experience. German tanks were precision instruments, each component carefully machined to fit specific positions. A connecting rod from cylinder 1 would not necessarily fit cylinder 7. A left-side road wheel assembly might have subtly different specifications than a right-side assembly. German engineering tradition valued precision, each part optimized for its specific function. The Americans had taken a radically different approach. They had sacrificed precision optimization for something else entirely: universal interchangeability. Over the following weeks, as winter gave way to early spring at Kummersdorf, the German evaluation team compiled increasingly detailed findings about the Sherman's design philosophy. What emerged was a portrait of industrial thinking that was simultaneously crude and sophisticated, simple yet profound in its implications. Richter spent days examining the transmission, creating detailed technical drawings for the Waffenamt archives. The 5-speed gearbox was robust rather than refined, built to tolerances that German engineers would consider sloppy. But those loose tolerances meant the transmission could handle dirt, debris, and thermal stress without binding. It could be serviced with common tools. Most remarkably, major components could be replaced without removing the entire assembly from the tank. "They have designed this machine for men with minimum training," Richter concluded in his technical notes. "A crew of average mechanics could maintain this tank under field conditions with basic equipment. Compare this to our own designs, which require specialized training and specific tools for even routine maintenance." The electrical system proved equally revelatory. Unlike German tanks, which used complex wiring harnesses with specialized connections, the Sherman employed a simple 24-volt system with standardized plugs and switches. Every light socket, every relay, every connection point used common components. A broken headlight could be replaced with a tail light. A damaged switch from the driver's panel could be swapped with a switch from the turret. Schneider, examining the wiring diagrams they had created, shook his head in disbelief. "This is automobile engineering applied to military equipment. They have treated this tank like a truck to be manufactured by the thousands, not a precision weapon to be crafted by specialists." "Perhaps," Weber replied quietly, "that is exactly their intention." The most striking discovery came when the team attempted to calculate the Sherman's maintenance requirements compared to German tanks. Using their extensive experience keeping Panzers operational in North Africa, they created theoretical maintenance schedules for both vehicles operating under similar conditions. For routine maintenance every 100 hours of operation, a Panzer IV required approximately 8 hours of work by trained mechanics with specialized tools. Critical components like the fine drive required periodic inspection that was time-consuming and technically demanding. The torsion bar suspension, while providing excellent performance, was complex to service and nearly impossible to repair in field conditions. The Sherman, by contrast, could complete the same routine maintenance in approximately 3 hours using basic tools. The vertical volute spring suspension could be serviced or repaired with standard wrenches. The final drive, while less sophisticated than German planetary gears, could be accessed and serviced without major disassembly. If these calculations are correct, Richter noted in a memo to Weber, the Americans have created a tank that requires less than half the maintenance man-hours of our Panzer IV. For a nation planning mass production and global deployment, this is a significant strategic advantage. But the evaluation revealed something even more profound than simple maintenance requirements. As the team catalogued components, measured parts, and documented assembly procedures, they began to understand the philosophical gulf between American and German military-industrial approaches. One afternoon in late March, Weber called his senior engineers together in the facility's briefing room. Spread across the table were components from the Sherman, meticulously labeled and organized. He had invited Oberst Heinrich von Richter, a logistics officer from the Army High Command, to review their findings. "Gentlemen," Weber began, "we have been examining this American tank for 6 weeks. We have measured every dimension, tested every system, evaluated every design choice. I believe we have discovered something more significant than the tank's combat capabilities. We have discovered a fundamentally different approach to mechanized warfare." He picked up a road wheel from the table. "This component can be installed on any position on this tank. It can also be installed on any other Sherman variant, the M4, M4A2, M4A3, M4A4. According to the manufacturing marks we have found, this wheel was produced at the Fischer Tank Arsenal in January 1943, but it will fit perfectly on a Sherman produced by any other American factory." Von Richter leaned forward, his logistics officer's mind immediately grasping the implications. Universal interchangeability. "Precisely," Weber confirmed. "Now consider what this means for their supply system. A single spare part shipment can support multiple tank models across different units. A damaged tank can be repaired using components from any other damaged Sherman. Field maintenance crews do not need to maintain inventories of model-specific parts." Richter added his technical perspective. "We have examined over 400 individual components from this tank. Of those 400, approximately 320 are completely standardized across all Sherman variants. The remaining 80 are engine-specific or hull-specific, but even those show commonality and within variant families." Schneider contributed the field mechanic's viewpoint. "Herr Oberst, in North Africa, I have seen Panzer IVs abandoned because a specific part was unavailable. The replacement might exist at a depot 200 kilometers away, but it was the wrong model variant. This American system appears designed to eliminate that problem entirely." Von Richter was silent for a long moment, studying the components spread before him. As a logistics officer, he had spent years wrestling with the Wehrmacht's supply challenges. German tanks came in dozens of variants, each with slightly different specifications. Spare parts were often model-specific, creating nightmarish inventory requirements. Units in the field might have 5 different Panzer models, each requiring unique components. "How many Sherman variants have the Americans produced?" Von Richter asked quietly. "Intelligence suggests at least 6 major variants," Weber replied. "But the critical point is that despite these variants, the vast majority of components remain interchangeable." "And our tanks?" Weber hesitated before answering. "Herr Oberst, we currently field the Panzer III in multiple variants, the Panzer IV in multiple variants, the new Panther, and soon the Tiger. Each has numerous subvariants with different engines, transmissions, weapons, and components. Very few parts interchange between models, and even within model families, components are often specific to production batches. The implications settled over the room like the cold March air outside. The Americans had not built a better tank in terms of armor or firepower. They had built a tank optimized for the logistics of global industrial warfare. They had understood something the Germans had missed, that wars were won not just by superior weapons, but by the ability to keep those weapons operational across vast distances and extended campaigns. There is more, Weber continued, pulling out a thick folder of processes, documentation. We have found marking systems on virtually every component, part numbers, production dates, factory codes, all clearly stamped and organized. The Americans appear to have created a comprehensive parts cataloging system that allows any mechanic to identify and order the correct replacement. He opened the folder, showing pages of technical drawings and parts lists they had created during the evaluation. Compare this to our own systems, where parts are often identified by informal descriptions or require expert knowledge to specify correctly. Von Richter picked up one of the technical drawings, studying the clarity and detail. This is mass production philosophy applied to military equipment. They are treating tanks like automobiles, standardized, interchangeable, designed for high-volume manufacture and widespread distribution. Which raises a troubling question, Richter interjected. If they can produce these tanks in large quantities, with simplified supply and requirements and reduced maintenance needs, what are the strategic implications? The question hung in the air, unanswered but increasingly urgent. The German team at Kummersdorf had set out to evaluate a captured enemy tank's combat capabilities. Instead, they had discovered evidence of an industrial logistical system that posed a far more serious threat than any single weapon design. As April arrived and testing continued, the evaluation revealed additional layers of American design philosophy. The Sherman's armor, while not as thick as German tanks, was well-sloped and consistently manufactured. Unlike the increasingly problematic quality control in German armor production, the American plates showed uniform hardness and reliable performance. The gun, while not matching the new German 75mm long-barrel weapons in penetration, was perfectly adequate for its designed role. More importantly, the gun mount was stabilized, allowing the gunner to maintain aim while moving, a capability no German tank possessed. The Americans had prioritized practical effectiveness over theoretical superiority. Even the crew layout revealed thoughtful design. The 5-man crew had clearly defined roles and adequate space to perform their duties. Ammunition stowage, while initially vulnerable, had been improved in later production models with added protection. The Americans were learning and adapting quickly, incorporating lessons from combat into ongoing production. They are iterating, Weber observed during one evaluation session. Rather than designing a perfect tank and then producing it unchanged, they are continuously improving based on experience. This welded hull model is already being replaced by cast hull variants. They have upgraded the ammunition stowage. They are developing better guns for future production. This too contrasted sharply with German practice, where design changes often required extensive bureaucratic approval and could disrupt production for months. The Americans appeared to have created a production system flexible enough to incorporate improvements without sacrificing output. By May 1943, the Kummersdorf evaluation team had compiled a comprehensive report on the captured Sherman. The document ran to several hundred pages, complete with detailed technical drawings, parts catalogues, performance data, and strategic analysis. Weber penned the executive summary himself, choosing his words carefully. The American M4 medium tank represents a fundamentally different approach to armored vehicle design, he wrote. While German engineering tradition emphasizes performance optimization and technical sophistication, American design philosophy prioritizes reliability, maintainability, and logistical efficiency. The Sherman is not technically superior to our Panzer IV in individual performance metrics. However, its design facilitates mass production, simplified supply chains, and reduced maintenance requirements that may prove strategically significant. He paused before adding the final, most troubling observation. Of particular concern is the discovery of extensive component standardization and interchangeability. The Americans appear to have created a parts supply system that could support armor operations across multiple theaters with minimal logistical complexity. If production numbers match intelligence estimates, this system could allow the Americans to field and maintain tank forces on a scale we cannot match with our current industrial and logistical capabilities. The report was classified and distributed to senior Wehrmacht commanders, weapons development offices, and logistics planning staffs. Some recipients dismissed the findings as exaggeration or misinterpretation. Others recognized immediately the strategic threat the evaluation had uncovered. But in the spring of 1943, with German forces still holding much of Europe and planning summer offensives in Russia, there was little appetite for fundamental changes to German industrial strategy. The Wehrmacht had committed to its existing tank development programs, the Panzer, the Tiger, increasingly sophisticated weapons that pushed the boundaries of technical performance. The American philosophy of simplicity, standardization, and logistical efficiency seemed almost pedestrian by comparison. Why would Germany, with its proud engineering tradition and skilled workforce, adopt methods that appeared to sacrifice quality for quantity? Weber understood the resistance his findings would face. As he prepared the final report for submission, he reflected on what the evaluation had taught him about the nature of modern warfare. The Sherman wasn't crude American engineering as propaganda claimed. It was sophisticated industrial philosophy applied to military requirements different from German approaches, but no less thoughtful in its execution. The Americans had asked a different question than German designers. Rather than asking, "How do we build the best tank?" they had asked, "How do we build a tank system that can win a global war?" The answer lay not in superior armor or more powerful guns, but in the unglamorous details of parts interchangeability, maintenance simplicity, and supply chain efficiency. As spring turned to summer at Kummersdorf, War Daddy 2 sat in a storage building, its evaluation complete. The tank had revealed secrets that had nothing to do with combat performance and everything to do with industrial warfare. But those secrets would remain largely unheeded by German military leadership, committed as they were to their existing approach. The evaluation team dispersed to other projects. Weber returned to examining Soviet equipment from the Eastern Front. Richter moved to a Panzer development program. Schneider went back to field maintenance duties in Italy. The comprehensive report they had produced was filed away, occasionally referenced but never truly acted upon. What none of them could know in that summer of 1943 was how prophetic their findings would prove to be. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By autumn of 1943, the strategic situation had shifted dramatically. The German offensive at Kursk had failed, Sicily had fallen to the Allies, and American industrial production was reaching staggering levels. Intelligence reports arriving at Wehrmacht headquarters painted an increasingly troubling picture of American armored strength. In October, Oberst von Richter found himself back at Kummersdorf, this time examining a second captured Sherman, an M4A2 variant seized from Soviet forces on the Eastern Front. The Soviets had received thousands of Shermans through Lend-Lease, and now the Germans were capturing them with increasing frequency as the Eastern Front stabilized. Von Richter had spent the intervening months since the first Sherman evaluation wrestling with logistics planning for the coming winter campaign. His experience had given him a different perspective on the American tank. He wasn't interested in its combat performance. He wanted to understand its supply system. "Hauptmann Weber," he said as they stood in the cold testing facility, "I need you to conduct a different kind of evaluation. I want to know exactly how many different parts this tank requires to remain operational for 100 hours of combat operations. Then I want the same calculation for our Panzer." Weber understood immediately what von Richter was seeking. "You want to compare logistical footprints." "Precisely. We are planning operations across thousands of kilometers. Every part we must transport is tonnage we cannot use for ammunition or fuel. If the Americans have truly created a more efficient supply system, I need to understand the magnitude of that advantage." Over the next 6 weeks, Weber's team conducted the most comprehensive logistics analysis ever performed on the Sherman. They calculated everything: fuel consumption, oil requirements, replacement parts frequency, maintenance consumables, even the weight and volume of a complete spare parts package for various operational scenarios. The results were more troubling than von Richter had anticipated. For a company of 17 Shermans operating for 100 hours in moderate combat conditions, the Americans would need to supply approximately 300 distinct part types. Many of these parts were universal road wheels, track sections, electrical components, engine parts that could support any Sherman in the formation regardless of variant. A comparable German company with 17 Panthers would require over 800 distinct part types. Worse, many of these parts were specific to production batches. A Panther manufactured in June might require slightly different components than one manufactured in August. The Germans' pursuit of continuous improvement and their multiple production facilities had created a logistics nightmare. The weight difference is even more striking, Weber explained during a briefing with von Richter and several other logistics officers. An American supply convoy supporting a Sherman battalion can carry parts that might repair any tank in the formation. Our supply convoys must carry variant-specific parts, meaning we need more tonnage to achieve the same operational support. Oberst Kaufmann, a supply officer from Army Group Center, studied the calculations with growing concern. "You're telling me the Americans can support more tanks with less logistics infrastructure?" "That is exactly what these numbers indicate," Weber confirmed. "But there's another factor we must consider: field repair capabilities." He directed their attention to a demonstration he had prepared. 2 damaged road wheel assemblies sat on a workbench, one from a Panzer IV, one from a Sherman. Both of these assemblies are damaged beyond field repair. However, watch what happens when we attempt to salvage usable parts. A technician approached the Sherman assembly. Using only basic tools, wrenches and screwdrivers that any field mechanic would carry, he quickly disassembled the damaged wheel. Several components were clearly destroyed, but others, bearings, bolts, mounting brackets, were removed intact. "These parts," the technician explained, "can be immediately installed on any other Sherman road wheel assembly. No fitting required, no modification needed." The technician moved to the Panzer IV assembly. The disassembly process was more complex, requiring specialized tools and careful measurement. When he finished, he held up several salvaged components. These parts could theoretically be used on another Panzer IV, but they would require fitting and possibly modification. The tolerances are tight enough that direct replacement is unreliable. "What you're describing," von Richter said slowly, "is that the Americans can cannibalize damaged tanks to keep others operational, while we often cannot." "More than that," Weber replied. "The Americans have designed their entire system around the assumption that parts will be swapped, mixed, and reused. A Sherman company could theoretically maintain operational strength by consolidating parts from damaged vehicles, even if those vehicles came from different production runs or different factories." Kaufmann leaned back in his chair, the implications washing over him. "We've been approaching armored logistics entirely wrong. We've focused on supplying perfect, new components to maintain our tanks in optimal condition. The Americans have focused on keeping their tanks functional by any means necessary." The meeting continued for hours, diving deeper into the logistics philosophy revealed by the Sherman evaluation. What emerged was a portrait of American industrial thinking that was both pragmatic and ruthlessly efficient. The Americans had accepted from the beginning that tanks would be damaged, that perfect maintenance was impossible under combat conditions, and that supply lines would be stretched thin. So they had designed a system that could function despite these realities. Components were overbuilt with loose tolerances so they could handle abuse. Parts were standardized so a damaged tank's components could support others. Maintenance procedures were simplified so minimally trained crews could perform them. Germany, by contrast, had designed tanks as precision instruments that required careful maintenance, specific parts, and skilled mechanics. This approach worked well in peacetime or in short campaigns where supply lines remained intact, but in a protracted war across multiple theaters, the American system held decisive advantages. "There's one more thing you need to see," Weber said toward the end of the briefing. He produced a thick manual bound in olive-drab covers. "This is the American Technical Manual for the Sherman tank. It was found in the captured vehicle." He opened the manual, revealing pages of clear diagrams, step-by-step procedures, and detailed parts illustrations. Every component was numbered and indexed. Every maintenance procedure was explained with illustrations simple enough for a mechanic with basic literacy to follow. Troubleshooting guides helped diagnose problems. Parts ordering information was clearly specified. "Compare this to our own documentation," Weber continued, producing a Panzer technical manual. The German document was dense with text, requiring advanced technical knowledge to interpret. Procedures assumed the reader had formal training. Parts were often described rather than diagrammed, requiring expertise to identify correctly. "The Americans have created a system that allows them to train mechanics quickly and deploy them with confidence. They can maintain equipment," Weber explained. "Our system requires extensive specialized training and assumes access to experienced supervisors." Von Richter took the American manual, paging through it slowly. As a career officer who had studied military history, he recognized what he was seeing. "This is how Rome conquered the ancient world," he said quietly, "not with superior soldiers or better tactics, but with superior logistics and administration. They created systems that could function across vast distances with minimal supervision. And the Americans have applied the same philosophy to industrial warfare," Weber agreed. By December 1943, von Richter had compiled his own report based on Weber's evaluation and his logistics calculations. His conclusions were stark. If current production trends continued, the Americans would soon field armored forces that, while not individually superior to German tanks, could be sustained in combat far more efficiently. The logistics advantage alone could prove decisive in extended operations. His report was classified, secret, and distributed to Army High Command, along with Weber's technical evaluation. The response was mixed at best. General Guderian, the Inspector General of Armored Troops, recognized immediately the threat described in the reports. He had been arguing for months that Germany needed to prioritize reliability and production numbers over technical sophistication. The Sherman evaluation provided hard data supporting his position, but other voices argued differently. Germany's strength lay in superior engineering and tactical skill. The solution to American numbers was not to copy their crude methods, but to produce even better tanks, heavier armor, bigger guns, more sophisticated systems. The Panther program continued. Tiger production expanded. New heavy tank designs moved forward. The fundamental question raised by the Sherman evaluation, whether Germany's approach to armored vehicle design was strategically sound, remained unanswered by institutional resistance to change. Meanwhile, in the real world beyond Kummersdorf's testing grounds, the American industrial machine was demonstrating the validity of its philosophy. By early 1944, Sherman production exceeded 2,000 tanks per month across multiple factories. The Germans, with their more sophisticated but more complex Panthers and Tigers, struggled to produce 500 tanks monthly of all types combined. More significantly, American tanks were appearing everywhere. British forces in Italy used Shermans. Soviet forces on the Eastern Front operated them alongside 34s. American armored divisions training in England prepared for the invasion of France. The logistical system supporting these forces was exactly what Weber and von Richter had identified: standardized parts, simplified maintenance, universal interchangeability. In March 1944, another captured Sherman arrived at Kummersdorf, this one an M4A3 variant with the new Ford GAA V8 engine. Weber's team conducted a rapid evaluation, curious to see how the design had evolved. What they found reinforced everything they had learned from earlier examinations. The new engine was more powerful but followed the same design philosophy: accessible, serviceable, built with loose tolerances that could handle battlefield conditions. The parts that had been standardized in earlier models remained standardized. The improvements that had been incorporated better ammunition storage, upgraded vision devices, improved track design, had been added without sacrificing the core logistics advantages. They are learning faster than we are, Richter observed during this evaluation. Each iteration improves combat performance while maintaining the supply system advantages. Meanwhile, our new designs often create entirely new logistics requirements. He was referring to the nightmare of supporting German, armoured units by mid-1944. A typical Panzer division might have Panzer IVs, Panthers, Tigers, various self-propelled guns, captured Soviet equipment, and captured French tanks all operating simultaneously. Each required different parts, different maintenance procedures, different technical expertise. The logistics staff needed to maintain separate supply streams for each type. An American armoured division using Shermans required essentially one supply stream, with parts that could support any vehicle in the formation. The strategic implications became painfully clear following the Allied invasion of Normandy in June 1944. As German and American forces clashed across France, the logistics battle became as important as the tactical fighting. American tank units that took losses could be rapidly replenished with replacement vehicles that required no special adaptation to unit procedures or maintenance systems. Damaged tanks were evacuated to field, workshops, repaired using standardized parts and procedures, and returned to service within days. The much-discussed Red Ball Express, the massive truck convoy system supplying Allied forces, could carry spare parts that supported any American tank on the front. German Panzer units, by contrast, faced mounting logistics paralysis. Replacement tanks often arrived in different variants than the units were accustomed to operating. Spare parts shipments included components that only fit specific models. Damaged tanks sat awaiting parts that might be available elsewhere, but couldn't be transferred due to variant incompatibility. The sophisticated engineering that German designers had prided themselves on had become a strategic liability. Von Richter, now serving with a Panzer Corps in France, saw the results firsthand. In August, his unit included Panthers, Panzer IVs, and a few remaining Panzer IIIs. A supply convoy arrived with parts, but the Panther final drives couldn't be used on Panzer IVs, the Panzer IV road wheels couldn't be used on Panthers, and half the components were for variants his unit didn't operate. Meanwhile, he watched captured American supply dumps being inventoried. Boxes marked Road Wheels M4 series contained components that would fit any Sherman. Crates labelled engine parts, Continental R 975, included standardized cylinders, pistons, and connecting rods, all interchangeable. It was the system Weber had described at Kummersdorf, now revealed in brutal operational reality. In September 1944, von Richter managed to visit a captured American armoured division's maintenance area before it was evacuated. What he saw there crystallized everything the Kummersdorf evaluation had identified. The American maintenance crews were using standardized tools and procedures to repair multiple Sherman variants simultaneously. Parts were organized in clearly labeled bins. Technical manuals were posted at workstations. The entire operation had the efficiency of an automobile factory which, he realized, was exactly the point. One damaged Sherman was being repaired using parts from 3 other knocked-out tanks, a turret from one, a transmission from another, road wheels from a third. The Icon mechanics worked quickly and confidently, mixing components without hesitation because they knew everything would fit. The repaired tank would be functionally identical to factory new production. A German repair facility with similar damage would have faced complications from variant incompatibility, parts that needed fitting, components that weren't quite interchangeable. The American system eliminated those complications through design. By late 1944, the strategic situation had become desperate for Germany. The industrial advantage the Sherman evaluation had identified was now fully manifest. American tank production exceeded German production by 5-1. More critically, American tanks stayed operational, while German tanks sat broken, awaiting parts or specialized repair. The Panther, which German propaganda still celebrated as a superior weapon, averaged less than 150 kilometers between final drive failures, exactly as post-war French tests would later confirm. Panthers were abandoned across France not because they were destroyed in combat but because they had broken down and couldn't be repaired under field conditions. Shermans, with their simpler systems and standardized parts, kept running. They could be maintained by crews with basic training. They could be repaired using parts from any source. They could be evacuated and returned to service rapidly. The logistics advantage that Weber and von Richter had identified in quiet testing facilities was now deciding the outcome of the war. In December 1944, as German forces launched their desperate Ardennes offensive, the logistics disparity reached its peak. German Panzer units advanced with minimal spare parts and inadequate supply lines. When tanks broke down, and Panthers broke down with distressing frequency, they were often abandoned because recovery was impossible. American armored units, even when retreating, maintained their logistics networks. Tank recovery vehicles evacuated damaged Shermans. Field maintenance units worked around the clock, using standardized parts and procedures. The same tanks that were knocked out one day were repaired and back in action within a week, something German units could rarely achieve. Von Richter, by now serving with Army Group B, compiled a final report in January 1945. It was a shorter document than his earlier work, written with the exhaustion of a logistics officer who had watched an army slowly strangle itself with overcomplexity. The American M4 Sherman tank program represents the application of industrial mass production philosophy to military equipment, he wrote. While we have pursued technical excellence in individual vehicles, the Americans have pursued systematic efficiency in their entire armored force structure. The result is that American tanks, though not superior in any single performance metric, operate within a support system that keeps them functional under conditions that would paralyze our more sophisticated vehicles. He concluded with a bitter observation. We examined captured Shermans in 1943 and identified their key advantage logistics. We understood what they had accomplished, but we lacked either the industrial capacity or the institutional will to respond appropriately. We continued building complex tanks that required extensive support, while our enemies built simple tanks with minimal support requirements. We lost the logistics war before the tactical war was decided. The report was filed with thousands of other documents from a collapsing Reich. It would be decades before historians fully appreciated what the Kummersdorf evaluations had revealed, that Germany's defeat in armoured warfare was as much about logistics philosophy as about tactics or strategy. The Sherman that started this story, War Daddy 2, captured in Tunisia in February 1943, survived the war. It remained at Kummersdorf through the facility's evacuation, was captured by Soviet forces in April 1945, and eventually ended up in a Red Army testing facility. Soviet engineers conducted their own evaluation, reaching conclusions remarkably similar to what Weber's team had found 2 years earlier. The Americans had understood something fundamental about modern warfare. It wasn't enough to design excellent weapons. You had to design weapon systems that could be produced in quantity, supplied across vast distances, maintained under adverse conditions, and kept operational through the chaos of sustained combat. The Sherman wasn't the best tank of World War II in any single category, but it was the best tank system, and, in total war, systems matter more than individual machines. Weber and Richter both survived the war. Weber was captured by American forces and spent 2 years in a POW camp, where he had considerable time to reflect on the weapons he had evaluated. After his release, he worked in the German automobile industry, applying some of the standardization lessons he had learned from studying Shermans. Von Richter was captured by Soviet forces and spent 8 years in captivity before being repatriated to West Germany. He never worked in military logistics again, but he gave occasional lectures at military academies about the importance of supply systems in modern warfare. His lectures always referenced the Kummersdorf Sherman evaluation as an example of how strategic intelligence could be accurate but still fail to change institutional behavior. In their later years, both men would sometimes discuss what might have happened if Germany had heeded the warnings contained in the Sherman evaluations. Could German industry have pivoted to simpler, more standardized designs? Could the Wehrmacht have reformed its logistics systems to achieve greater efficiency? Would it have mattered given Germany's resource limitations and strategic overextension? These questions had no clear answers, but both men agreed on one conclusion. The Americans had won a war with logistics as much as with weapons, and the Sherman tank program was the clearest example of that victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.